All right, folks, I'm ready to get started. Welcome back, everybody. Welcome to the 6th week of class together. So we are heading towards the midway point. So hang in there. I know that this is a tough time for you. You've passed through the first big obstacle in this course, but I'm sure you're being tested in your other classes as well. So just keep your head together, keep your head in the game. Make sure that you're managing your time properly. If you have extra time, use that time to get some work done. Every moment of free time is an opportunity. The more you spend kind of getting ahead any chance you get, the more opportunities you have for those things that may pop up and distract you from the things you have to get done, i.e. an emergency, or that's the worst case scenario, but just on a good day, your friends call you up and want you to go to a concert or whatever. I don't know. So when you're in school, it's all about just making this your priority and just taking care of as much as possible when you can in order to make this work out, in order for you to have some peace of mind, in order for you to feel good about what you're doing here, so you can walk away from the semester feeling like you've accomplished something, not harboring regret over just dropping the ball, because that can really taint your ability to enjoy the free time you get once this is all over. And it will be over. This class will end. You will walk away ideally feeling good about what you accomplished here, and you'll have a great summer. So make sure that while this is happening, this is what is happening for you. Make it a priority for yourself, and things will work out. Are there any questions you want me to address about anything before I move forward with today's material? All right, yeah. So chapter 5 we will not finish today. So yeah, it's kind of a big chapter, so we'll continue actually on Thursday, and there will be a small section I'll cover next Tuesday if I don't get to it at the end of Thursday. So, but if you're interested in starting the homework, is that what you were asking about? Yeah. Okay, yeah, I'll open that up today. Yeah, I'll open it up today and just have it there. But I mean, we're certainly not going to cover all the relevant stuff yet. So you might want to stay away from it just so you don't get confused, unless you get ahead of yourself. Which but I will open it up. Yeah. What do you mean? Oh yeah, I'm planning for there to be 3 this time. No, man, that was a mistake. That was an error. I was creating 2 exams at the same time. I meant to copy and paste one question to another exam, and I accidentally pasted it to the same exam. It happens. It's life. But it doesn't matter, because in the end, either you know the information or you don't. The exams are a cross section of the information we cover in class. They by no means cover everything we cover. You're expected to learn everything, and then the exam is meant to just test you on your overall understanding. Either you know this stuff or you don't. So it doesn't matter what's on the exam. Either you go in there prepared or you don't, and that will dictate how you do on the exam. So it could be just one question next time, 15 times. It won't be. I would never do that to you. I'll do it to other people, though. I like you guys. Anyway, other questions? All right, then let's move forward, because again, like I mentioned last time, this is foundation for everything we're doing from this point forward. Your understanding of what's happening in this chapter will provide you just the basic insights you need to understand everything else that we do once we start kind of building and applying the model to gain the insights that you can gain from these models in order to be able to manage properly in different market settings that cover the spectrum of competition, be it as competitive as possible in what we call the perfectly competitive case, or the least competitive possible in the monopoly case, or in the in-between cases. But in order to get to that, we have to, again, establish the basic nature of production, which we do via the production function, which we started talking about last time. We'll continue talking about that today. We have to establish the nature of production in the short run versus the long run. And then once we have all that down, then we kind of translate that to cost. What does that mean for costs? And then once we have all the relevant costs in place, then we can start using that framework to analyze optimal decision making by firms in various market contexts. So This chapter will take us through to the end of costs, and as I mentioned, like we're going to try to finish it by Thursday, but if we don't, I'll have a slight portion of it covered on Tuesday, but then we'll cover all of chapter 6 on Tuesday, because chapter 6 is not very long and it's not very complicated. It's more like practical stuff, like how does a firm like practically acquire the inputs that you need in order to minimize costs, and sort of the various issues related to that. How do you get, so we talked about the two main roles of the manager in the production process, which is to make sure that employees are working on the production process, on the production function. So that's a whole other thing, like actually trying to get folks to work at the level you need them to work. So that's slightly touched upon here, but that's, if you're a management major, that's covered more in your other classes. And then the other role is to choose the right input mix. How do you make sure that you are using the right amounts of either capital or labor, given the needs of your production process, in order to minimize the cost of your production? So issues related to those two things will be covered in the next chapter, and then after that, chapter 7, which we'll cover on Thursday of next week. So that's a small chapter as well. We'll cover issues related to like what makes one industry more competitive than another. What do we have to gauge that sort of difference in competitiveness? Like what kind of tools do we have? What kind of fail safes do we have as far as like government intervention that can maybe address some of those issues? So more practical stuff. So definitely 6 and 7 are less abstract as far as like the theory that ultimately gets you to the principles. And so those are actually really good chapters to use for mini paper stuff. So even though everything is really good to use for mini paper stuff, because if you're thinking about this enough and you've read your case thoroughly enough, you can figure out a way to explain a part of your case via the theory that we're using, or address some of the issues that the firms are facing in the various cases, etc. So as long as you're in tune with like the theory and what it means, and just using it as sort of a filter to explain or analyze something within the cases, you can write mini papers based on any chapter. But for those people that are less sort of connected to the practical implications of the abstract nature of the models that we use, again, chapter 6 and 7 tend to have more practical information in them that can help you to sort of just make some easy linkages between what's happening in your case and what you're expected to write on the paper. So, and also ideally it's happening, at least for this class, it's happening between exams, but also ideally that's the same for your other classes as well. So maybe you do have some time to kind of knock out some papers. Again, it's a good idea to knock these out sooner rather than later, so that at the end of the semester, you're basically done with the paper. And people that do that love it. By the end, they're like, great, I didn't have to do anything at the end. It's just done, and I get a grade that I deserve for it, and I'm happy. But there's always that group of people that just leave it to the last moment, and like the last 3 options are the ones they choose, and some of them don't even make it. So some of them like write 1 or 2 papers, which is silly because you wind up losing some extra, like necessary credit overall in the course by not turning those papers in. And generally it's going to be the people that you don't see here. But not everybody. Some of them are doing exceptionally well, and they feel comfortable just not being in class, and that's, everybody has a right to do that. But that always does happen. Try to avoid it. I'm sure the majority of you that I see on a regular basis, I see a lot of familiar faces in front of me, of course. You obviously are dedicated to doing well in this course, so you're likely knocking these things out. I'm not checking because it becomes just a whole burden to like kind of go through all the mini papers all the time. So who's submitting what, like I just leave it all till the end, and then just kind of make it the big task at the end once I get the papers in, to grade all the mini papers, grade the final paper, and get your grades for that ready, so that what your standing is going into a final. So that's my approach for that. So just know that if you're submitting the papers, they're there. They're digital lockers. Digital lockers keep your information indefinitely. So if you've submitted papers, they're there. They will be graded. You will get credit for them as long as they meet the 2 to 3 page requirement. And that's basically it. As long as I meet the 2 to 3 page requirement, and you didn't just submit 2 to 3 pages of a blank document, which people have done in the past. All right. Anything now, given everything I just talked about, you'd like me to address? All right. So let's move forward then. Again, we're talking about the production function, and that's basically it today. We'll talk about what we've talked about. We'll expand what we've talked about a bit, and then we'll start getting into the long run situation. The long run situation obviously is more complicated because, again, what defines the long run versus the short run is that in the long run, all inputs into production are variable, can be chosen with discretion, and thus that makes production a function of two variables. So then you have a three-dimensional relationship, capital and labor being the two inputs that we consider in this class. And so when you have that, the best way to represent it is via, at least in terms of what we do in this class, is via a similar framework to how we analyze the decision to consume via the indifference curves and the budget constraint. You're going to have a very similar framework, and all the properties of that model, which we call the rational consumer choice model, will translate over as far as like the mechanics of how it works and the intuition of how it works. So if you got that stuff down, it should help you to understand this model that helps us to understand how firms can optimally choose their inputs in the long run in order to minimize their costs, given like targets for production, etc. And so I'll start building up that model today, and then we'll continue on Thursday, and then we'll get to costs on Thursday, and then we might finish the chapter, we might not, we'll see. All right, so just based on what we've covered already, again, when we're talking about production, we use what's called a production function, which is an engineering relation that defines the maximum amount of output that can be produced with a given set of inputs to just sort of simplify the process in order to be able to gain the insights we're looking for from it. So we establish quantity of output as a function of both capital and labor. In the short run, the short run is defined as a time frame in which at least one input into production is fixed, so the firm is not able to adjust that input into production. And once the firm is able to adjust all factors of production, then they are by definition in the long run. So anytime there is an inability to adjust all inputs, be it capital, be it labor, generally we assume it's capital in this class, then the firm is in the short run. And all these concepts are going to have huge implications for cost. They're going to have huge implications ultimately also for how competitive an industry can be. So everything's related here. All right, so we have measures of productivity that we look at, which are relevant to understanding, again, ultimately costs. And so we look at the overall amount of output that can be produced, which is the total product. We look at the average product of each of the inputs into production. If I have 20 people and I'm producing 100 units, what's my average product? Well, it's 5 per person. We can look at average product of labor, which I just did. We can look at average product of capital. And then, of course, we look at marginal product. What is the extra amount of output produced by employing one more unit of labor, of capital? So that's our marginal product of capital, marginal product of labor. The change in the quantity with respect to the change in our input, be it capital or labor. And it also winds up being the derivatives of the production function with respect to capital and labor. So today we're also going to cover derivatives again, just because we'll start taking derivatives past today. So I'll just do a quick review just so you remember the mechanics of it. For those of you that might be a little bit rusty on it. I know some of you don't need that, but I hope you'll just be patient. It won't take long. But at the very least, I want to catch those people up that maybe have forgotten a bit about how to just take derivatives. I want to make sure everybody knows how to do it. The book is very strange in that it doesn't, it presents derivatives in very general ways and basically expects you to memorize equations, which is bad. It was a terrible approach. Know how to take the derivatives, understand how I get from one equation to the resulting equation that I need you to get to in order to get the result I need you to get, versus trying to memorize equations out of the book that are derivatives, because that's just a recipe for disaster. You're just memorizing equations. You don't understand where they came from. You don't understand what they are. Like, and people that aren't plugged into the course, like right before the exam, like they'll email or something and they'll say, oh, can we get an equation sheet? Because there's all these equations in here. It's like, no, you should understand, if you've been plugged in, if you've been listening to me, that everything that the book is asking you to memorize, you can just derive by, the basic approach that you learned in your 308 class, or one. Is it 308? No, this is 308. 108. Is it 108 or 103? 103. It's 103. Math 103. There you go. Which is a business calculus course in this school, unless, in case you took it elsewhere, I'm sure it was called something else, whatever. Maybe you took actual calculus, which is good. You should take the actual courses at some point if you get a chance, and it'll help you. Anyway, so we're going to take some derivatives. So to get the marginal products, we have to take derivatives of the production function, either with respect to capital or labor. In the short run, we assume that production is only a function of labor, and so you only take the derivative of the production function with respect to labor to get the marginal product of labor, to figure out, if you hire one more person, how much extra output will that person produce? All right, so based on the general production process that we model to gain the basic insights that the course provides, there's a standard sort of pattern that's followed. We assume that initially, obviously, the firm is starting out with 0 employees. They hire 1 employee, they hire 2 employees, they hire 3 employees. Like that first employee had to do everything. The second employee helped that person. They started dividing up the task. Third, same thing. So the first few employees that are hired start dividing up the tasks and actually increase efficiency as far as production. So the marginal product, the extra amount of output produced by employing additional workers, will be increasing initially over this initial range, just based on how we assume production to go in general. So there's increasing marginal returns to labor initially as firms hire their first few employees. Again, they divide up the tasks, they benefit from specialization, the division of tasks. So this is our total product curve. Again, it tells us the total amount of output with respect to how much labor is being hired, and we're assuming that we're in the short run, we're looking at total product. So we're holding capital constant in our general specification. And this blue curve here is the marginal product curve, and it is just basically plotting the slope of the total product curve. So it's telling us that from point A to point E, the marginal product of capital is increasing. So we have those increasing returns, marginal returns to labor, as those first few employees are hired. By assumption, it's just assuming that it's up to 5 people, but that's obviously just by assumption for this particular example. But of course, the short run has a limitation, and the limitation is that only so much capital is available, and so as more and more people are hired, then they run up against that wall where the factory space starts to become limited. The amount of machines available to produce start to become limited. And so, although as you hire more folks past a certain point, in this case past 5 employees, the extra amount of output they produce will be positive. The extra amount of output they produce will be less than the prior people hired. So then you'll have a decreasing marginal product, which tells us that as far as our production process goes, we have decreasing or diminishing marginal returns. And it's all because of the short run situation, because capital is fixed. And then eventually you could potentially get to a point where you hire so many folks that the total product starts to actually decrease. And that's the point where marginal product becomes negative. And so here we see that our marginal product curve increases, then decreases. Increases when we have increasing returns to labor, and then decreases when we have decreasing returns to labor. And then there's also one other curve here, which is our average product curve. And we see that our average product curve is related to marginal product in the sense that if the marginal product of capital is greater than the average product of capital, then it's going to bring up the average, because again, you're you have some average, you're adding a number to it that's bigger than the average, it's going to pull the average up. Even when we hit decreasing returns, we see that the average product is still increasing because the average product is still below the marginal product over this range here. But then at this point here, that changes. Average product is at its maximum when marginal product crosses it, and then marginal product starts to pull down the average product. So average product starts to go down after that. Why that relationship is important will become clear when we're talking about costs. The average costs are important for supply decisions. The marginal products are important also for supply decisions, but also for considering profit maximization. So everything that's being established here is, again, foundational for just your overall understanding of all the insights that we gain as we move forward, using this framework as the basis for analysis. So just try to get this stuff down the best possible now. All right, so as I already mentioned, the role in the production process for the manager is to make sure that the firm is operating on the production function. If you have a production function and your employees aren't working on it, then all the insights you know about production in general go out the window. So obviously that's a challenge that most managers face. And then the other one is using the right level of inputs. How many people should I hire at any given point? Well, in the short run, we have a way of figuring that out. We look at the extra benefit of hiring a person or extra benefit of employing an additional unit of capital versus the extra cost of hiring another person or employing extra units of capital. So the benefit of hiring an extra person or employing an extra unit of capital is called the value of the marginal product. Either the value marginal product of labor or the value marginal product of capital. And essentially, it's just their marginal product times the price that the good can be sold at that's being produced in the firm. So that's the value of the marginal product of an input into production. So we established that the firm, we will hire an additional inputs up until the point where the value of the marginal product is equivalent to the cost. So we assumed in our basic example that the wage was fixed at some amount. We know that marginal product has that hump-shaped curve, again, because increasing returns help us to increase marginal product first, and then decreasing returns cause us to decrease marginal product afterwards. And so this is essentially the marginal product of labor curve multiplied by just the price of what can be sold. So you're going to get the same shape. And so it's only over the decreasing range of that curve that relationship is relevant, where you're comparing the value of the marginal product to the cost. Because over here we see that the value of the marginal product of labor is equal to the cost at this point here as well. But hiring additional people because of increasing returns will actually increase the value of the marginal product above the cost. And so the marginal benefit exceeds marginal cost, which means you should keep going in the activity that you're engaging in this case, hiring workers. So it's only over the decreasing range of the value of the marginal product of labor curve that relationship becomes relevant. And therefore, the decreasing range of this curve actually winds up representing the demand for labor in labor markets by firms. Firms, again, have a willingness to pay for varying amounts of labor, and it is represented by the downward sloping side of the value of the marginal product of labor curve, which is the demand for labor. And again, they will hire at the point where the extra benefit of hiring a person equals the extra cost of hiring a person. Prior to that, we see that the extra benefit is greater than the cost because, again, the value of what can be produced and sold is greater than the cost of the employee versus past that point where the employee costs more than what they are benefiting the firm in terms of revenue. So that's how a firm chooses the profit maximizing amount of an input in the short run. And in the long run, we'll talk about how that works. And we'll look at the the calculus of this once we establish how to take derivatives. All right. So having established this general relationship between inputs and production and sort of the general characteristics of production, then we using graphs and using tables. Now we'll jump to the math, the algebra. And so representing that relationship between inputs and output can differ depending on the nature of the production process being considered. So there's a very standard case that will reflect what we just talked about, but then there's like extreme cases that don't reflect what we just talked about. So we'll cover those extreme cases first right now and how we could represent those mathematically, and then we'll do the calculus stuff, and then we'll look at the actual production function that we consider in this course, which does reflect the characteristics that we just discussed. So, okay, the underlying notion of a production function can be expressed mathematically. In this section, we highlight some more commonly encountered algebraic forms of production functions. The most simple production function being a linear production function of inputs. So a linear production function will take some very simple form, as you see here, where you just have capital times some constant plus labor times some constant equals the amount of output. With a linear production function, the inputs are perfect substitutes, meaning that they each have some level of productivity, and that never changes regardless of how many you're using. And so as long as you know what their productivity is, you can just substitute them in the same proportion, regardless of how much you're producing, and that relationship will stand versus what we'll see later with the more common case where depending on the amount of labor, the amount of capital you're using, their productivity will vary. And so you will not be able to substitute them in fixed proportion. So suppose it takes workers at a plant, let's say 4 hours to produce what a machine can make in 1 hour. In this case, that means that workers are going to be 1/4 as productive as a unit of capital. So a unit of capital will be 4 times as productive as 1 unit of labor, which could be represented by just having the constant on capital be equal to 4 and the constant on labor be equal to 1. So the linear production function will take this form here, 4k plus L. This is the mathematical way of stating that capital is always 4 times as productive as labor, and so you can just plug in the amount of capital and labor that you have, and you can figure out what the output would be there. The other extreme case is a case where you can't substitute between the inputs. You can only use them together in a certain fixed proportion, versus the other two, versus the linear production function, where they are perfect substitutes. You can substitute for each other, so you can just have labor producing, or you can just have capital to produce. Whereas in this situation, you can only have a certain amount of each in order to get to the amount of production that you're looking to achieve. So we represent that by this mathematical relationship, which basically establishes that the amount of output that can be produced is going to be equal to the minimum of either of these two numbers. Whichever of these two numbers is lower represents the amount of output that can be produced. So therefore, let's say it was 1 and 1. If you try to increase your capital, tenfold, that's not going to increase your output, because you need labor and capital together in order to increase the amount of output. A and B, of course, are constants. So the Leontief production function is also called the fixed proportions production function. Suppose the production function we're talking about is for a word processing firm, a firm that just types out documents. So in this case, the constants on each of our inputs are going to be equal to 1, because you need one person and one keyboard in order to increase your production. If you hire a lot more people and there's only one keyboard, you're not going to increase production at all. If you buy a bunch more keyboards and you only have one person, it's not going to increase production at all. So if we let K be the number of keyboards and L be the number of keyboarders, the production function implies that one keyboarder and one keyboard can produce one paper per hour. Two keyboarders and two keyboards can produce two papers per hour, and so forth. Keyboarders and keyboards must be used in fixed proportion of one keyboard for every keyboard. And that's so there are production processes like this. And again, these are extreme cases. These are like how extreme you can get in the spectrum of production. And so we have to like just bring them up in order to establish like how we deal with these cases. But again, ultimately, we're just going to be dealing with the in-between cases of both of these. Just a quick demonstration problem on how to sort of work through the Leontief production function, which I would expect you to understand. So the engineers at Morris Industries obtained the following estimate of the firm's production function. It's a Leontief production function, and it looks like this. So again, output is going to be the minimum of these two numbers. How much output is produced when 2 units of labor and 5 units of capital are employed? What was that? It is not 2. It is not 6. It is not 3. It is 8. Who said that? Whoever it was, you were right. It is 8, right? You plug in 2 units of labor, that's 8 there. You plug in 5 units of capital, that's 15. So obviously, you can only produce the minimum of those two numbers. So the minimum is going to be, in this case, 8, right? So that's how much can be produced given the nature of this production process. So it's kind of a strange one, right? So like if you had one labor and one unit of capital, you can produce 3 units. If you increase your capital by 2 units, that'll get up to 6, but you could still only produce 4 units based on the fact that you only have one labor. You need to increase them both in fixed proportion. It's not 1-to-1 here, but it is still in fixed proportions. But again, it is an extreme sort of case of what production can be. So again, yeah, so here we're looking at the minimum of the 2, which is equal to 8. Since the minimum of the numbers is 8, we know that 5 units of capital and 2 units of labor produce 8 units of output. All right, so that's the Leontief production function. Make sure you understand it. Just make sure you understand like why we cover the two cases in order for you to truly understand the common case that we will be tracking. All right, anyway, so in order to move forward with the math that you'll need to be able to measure productivity from the production function that we'll be looking at, you're going to need at least to remember how to use exponents, remember how to use derivatives. So let's just cover that stuff. So I quickly like to cover the properties of exponents for those of you that forgot. So again, if you have some, like let's say you have some number b, so let's say it's 8. B is 8. 8 raised to the x power, 8 raised to the y power. So you have the same number being raised to 2 different powers. Let's say it's 3 and 4. Then that tells us that that is equivalent to 8 being raised to the sum of the exponents, right? So it would be 8 raised to the 7th power if they were equal to 3 and 4. If you have some number b raised to some power x divided by that same number b raised to some power y, that is equivalent to that number b being raised to the difference of the 2 powers, right? If you have some number b being raised to some power and then you raise that entire expression to some other power, then you essentially are multiplying the exponents. So this is equivalent to b raised to the product of the 2 exponents. If you have 2 numbers b and c being multiplied and then the entire product of that being raised to some power x, that is equivalent to each of the 2 numbers b and c being raised to the power of x and then being multiplied together. Properties of exponents. If you have a ratio of 2 numbers, b to c being raised to some power x, that is equivalent to the numerator being raised to the power x divided by the denominator being raised to the power of x. Obviously, any number raised to the power of 1 is equal to itself. What is any number raised to 0? 1. So any number raised to 0 is equal to 1. And of course, any number raised to some negative exponent is equivalent to 1 over that number raised to the exponent. Some review there for you. All right, let's talk about the derivatives. So the main problem of differential calculus deals with finding the slope of a tangent line at a point on a curve, right? So you have obviously just a regular line that has a constant slope, and it's really easy to figure out what the slope of the line is. We know that it's constant along it, and it's just the rise over the run, right? The change in y over the change in x. But when you have curves that aren't lines and they're just like kind of moving around, we know that there's a slope there and it's changing, but we can't use a rise over run type of approach because we know that the rise over run is changing over the range. So we need a different approach to be able to figure out, well, how is this relationship changing at a particular point along this curve that is changing? So we use the slope of a tangent line to estimate that. So in high school geometry, a tangent line or tangent to a circle is defined as a line that meets the circle at exactly 1 point. So those are tangent lines there. The idea of a tangent line is not very useful for other kinds of curves, though. So here we have a tangent line that is touching this curve at this point here, but it is cutting through other parts of the curve. So the definition of the tangent line is not clear-cut when you have a curve like this. And so we need to go a step further with the tangent line approach in order to be able to get to the calculus method of figuring out how much a curve is changing at any given point. To obtain an adequate definition of a tangent line, we use the limit concept and the geometric notion of a secant line. So I'm not going to talk about limits right in this class mathematically, but it was something that was covered in your class. I don't expect you to know limits. The whole point of understanding limits is just to get why you can use the derivative approach, why it is legitimate. And so that's why we learn limits. And so you should understand limits for that reason. If you're not going further in using mathematics for who knows, whatever it is you might end up doing. So in order to sort of marry the limit concept with the tangent line concept, we use the concept of a secant line. A secant line is just a line that intersects a curve at 2 or more points. So let's say we want to define a tangent line at point P. So here we've got a parabola. It's just like an x squared relationship, basically. And we are looking to define a tangent line at point P. So at point P, we're looking to define a line that can then, if we get the slope of that line, can give us an estimate of how this relationship between y and x is changing at that point. So we can start with this one secant line. It cuts through point P, and it also cuts through the parabola at point Q. Q is some different point on the curve, so PQ is a secant line since it intersects the curve at 2 points. Now, if Q were to move along the curve and approach P from the right or the left, the figure below shows the typical secant line. So let's say, again, we're looking for the rate of change at P, and so we could estimate it based on the slope of this line here, but that would be a very sort of broad estimate, and it wouldn't necessarily tell us exactly what's happening at this point. So we could say, well, what if we got closer and closer to P? So we had this line, which is PQ prime, which is a little bit closer, PQ double prime, again, a little bit closer, PQ triple prime, a little bit closer, and then finally we get to this line here from the right side that is tangent to point P, is just touching point P. We can do the same thing on the other line, kind of look at the secant lines that kind of approach that point. Again, you've got this secant line, and this one gets closer, this one gets even closer, and then finally we approach once again this tangent line that is just touching point P. In both cases, the secant lines approach the same limiting position, that tangent line. The common limiting position of the secant line is defined to be the tangent line at the curve at P. The definition can be applied to curves in general. All right, so the slope of a curve at a point P is the slope, if it exists, of the tangent line at P. So if we get the rate of change of that line that's tangent, that's the limiting position of these secant lines, then it'll give us a really great approximation of how the actual curve we're interested in is changing at that point with respect to the relationship that we are studying. So consider the curve, again, f of x equals x squared, and the slopes of some secant line PQ, where like the point P is at the coordinate 1, 1, let's say. So if P is at 1, 1, and then Q is at 2.5, 6.25, we can get the slope of this secant line by, again, taking the rise over the run, so the difference between the highest point and the lowest point. So 6.25 minus 1, so this has a y value of 1. And then the difference in x's is, of course, 2.5 for this point minus 1 there, so that's what we have there, and that gets us to the slope, which is equal to 3.5. So that line has a slope of 3.5, again implying that you change x by 1 unit, that means y changes by 3.5 units. This table here shows us the slope of all the secant lines. If we were, again, to get the slope of the secant lines as we approach that point P. So again, initially, the furthest secant line that's represented by PQ has that slope of 3.5. If we get closer to P with closer and closer secant lines, then we see the slope starts to approach 2. So it goes from 3.5 to 3 to 2.5 to 2.25 to 2.1 to 2.01. And so the closer and closer we get that secant line to that point, eventually converging on the limiting position of this tangent line, we see that the slope of that line approaches 2.2, essentially 2. So the limit of the slope of the secant lines is an approximation to the rate of change of a curve, which we call the derivative. So that is what the derivative is. It's the slope of that tangent line that is the limiting position of the secant lines. Once you understand that, there's some math that helps you to get to some shortcuts on how to estimate the slope of the limiting position, the derivative, at any given point. So that's what I'll cover. I'll cover the basic rules of taking derivatives with your understanding that, again, the result that you're getting is going to give you an equation for how the slope of that tangent line is changing as you're moving along the curve. So that's what's happening behind the scenes. It's important to know what's happening behind the scenes because you don't just want to do things blindly. You want to know what you're doing. But in the end, if you just know the shortcuts that I'm going to establish here with the basic rules of taking derivatives, that's all you'll need in this class to take the derivatives I need you to take. But it's better for you to understand what you're doing versus just blindly doing something you memorize, not having any understanding of it. So that's why I went over all that. And again, I'm not going to test you on what the nature of a derivative is. I'm just going to have you apply the derivative. So this is what I need you to know: the basic rules, how to take the derivatives. All right. So if c is a constant, then the derivative of a constant is equal to 0. So we denote the derivative by d dx. So in this case, it's dc dx, the change in c with respect to x. Well, if c is constant, that means that c is not changing as x is changing. We can represent a constant function by just a horizontal line in this case, because c again represents f of x. The function, so the relationship between x and y is constant. As x is changing, nothing is happening with y, and therefore the rate of change of this line, this relationship is 0, because again, as x changes, nothing's happening with y. The slope of the secant line is constant. So again, the derivative of any constant is equal to 0. Again, d dx denotes the derivative. Also, if you have some function f of x, you can denote a derivative as f prime of x. Examples of derivatives of constant functions: the derivative of 3 is equal to 0. So this could be equal to 3. F of x equals 3. And the derivative of that is equal to 0. The derivative of the square root of 5 is equal to 0. The derivative of some number raised to some crazy power is equal to 0, because that's just a number. And that means that it's a constant function. There's no variable in there. And so the derivative of a constant is equal to 0. The next rule gives a formula for the derivative of x raised to some constant power. This is what we call a power function. So the rule for taking a derivative of this kind of function is to multiply the function by the exponent and then just subtract 1 from the exponent. And that gets you to the equation for the slope of that tangent line that will change as you move along x. Because, that's what we're trying to figure out. That how is the slope changing along a curve? That can't easily be gauged like a line can, where the slope is constant. So again, if a is any real number, then the derivative of x to the a is equal to, again, you're multiplying it by a, you're multiplying it by the exponent, then you're just subtracting 1 from the exponent. Example, f of x. X is raised to the first power. We don't see it, right? But it's there. So essentially, you multiply this whole thing by 1. You subtract 1 from the exponent, so you're left with x raised to the what? The 0 power, which is equal to? It's equal to 1, right? So if you have any variable that doesn't have a power, then the derivative of that is going to be equal to what? 0, right? I'm sorry, no. It's going to be equal to 1, yes, exactly. Because you're going to have x raised to the 0 power, which equals 1, times the 1, which is equal to, of course, 1. X raised to the negative 10th power. So you're going to multiply this by negative 10, and what's the exponent going to be? Negative what? It's not negative 9. Negative 11, right? Negative 10 minus 1, negative 11. Yeah, you have to be careful. That's why I like to go through these problems, just to kind of get you in that mindset, because you can easily make that mistake. We've all made it. So negative 10 times x raised to the negative 11th power is the derivative of this function. Again, this equation tells us how the slope of that tangent line is changing as we're moving along that relationship, right? You're putting in different values of x, and as you put in a new value of x, it tells you, okay, so at this point, the rate of change is whatever, and it is, again, an approximation to that tangent line that is the limit of the secant line. So that's what's happening behind the scenes, but this is all you need to know as far as like taking the derivative. You should know what it means, like not just like, I did this and it's right, but like, what does it mean? It means what it is. It's so powerful. Like Isaac Newton developed this, like he spent a lot of time alone, like 20 or 30, maybe 60 years alone in a house with just like a servant. And he came up with something that changed the world. I hear he was a total asshole, though, which, that will tend to happen, with people that are kind of like shut-ins. But, you could change the world by being that sort of person, apparently. Not advocating for it, but, it's like spending time on your own is important to accomplish great things, is ultimately, like, the moral of that story. And this has changed our world. Like we wouldn't be able to get off the planet if it wasn't for this stuff. Like we wouldn't be able to build skyscrapers if it wasn't for this stuff. Like huge bridges, etc. Like the world has changed. All right. So sometimes a function can be rewritten so that the proper form for the rule applies. So let's say you have some function 1 over x raised to the 10th power. Well, this is a power function, but you don't necessarily have it in the form you wanted. So using the properties of exponents, you can get it into the proper form. So what is this equivalent to? X raised to the negative 10th power. Yes. If you said x minus 10, I'm sure you were just describing it a little differently, but just describe it correctly. X raised to the negative 10th power is exactly correct. Just given the properties of exponents, and now we can just take the derivative easily as we did there, which was this was that same equation. Okay, so x raised to some the square root of x is equivalent to x raised to the 1/2 power, right? Just like the cube root is x raised to the 1/3 power. So if you have this, you can't easily take the derivative, but if you get it into the form of x raised to the 1/2 power, then you can just take the derivative, 1/2 times x raised to the 1/2 minus 1 power, which is equal to 1/2 x raised to the negative 1/2 power. If you have this expression here, you've got x times the square root of x. What you essentially have is x times x raised to the 1/2 power. You've got that same number, x, being raised to the power of 1, and then multiplied by x raised to the power of 1/2. So based on the properties of exponents, what do we know this expression to be equivalent to? X raised to x raised to the 3/2 power, right? Exactly. You have x raised to the first power times x raised to the 1/2 power, so you essentially have x raised to the power of 1 plus 1/2. Yeah. And 1 is equal to 2/2, so then, 2/2 plus 1/2 equals 3/2. So x raised to the 3/2 power there. And now you can take the derivative. So you multiply the whole thing by 3/2, and then subtract 1 from that exponent. So that's going to get us to 3/2 x raised to the power of 1/2 for that derivative. Constant factor rule. So if f is a differentiable function, and c is a constant, then that constant times the function is differentiable, and the derivative of that function is equal to the constant times the derivative of the function. So a constant times the function equals, the derivative of a constant times the function equals the constant times the derivative of the function. Essentially, when you're taking the derivative and there's like some coefficient there, some number, you just leave that number alone and just take the derivative as you normally would. And then, if you have to multiply that number by something, do so to simplify the expression. So again, the derivative of a constant times a function is the constant times the derivative of the function. So you've got, again, this expression here. What is the derivative of this? 15x squared is exactly correct, right? We are multiplying 3 by 5 there. Just as far as what I just said, again, the derivative of this constant times a function is equal to the constant times the derivative of the function. So you basically just leave the 5 there. And now we take the derivative of x cubed, which is 3 times x raised to the power of 3 minus 1, right? So then that 3 is multiplied by the 5, which gets us 15. And then again, we subtracted 1 from the exponent, so we have 15x squared there. Sum or difference rule. If you have the derivative of two functions, f of x and g of x, that are either being summed or subtracted, then that's equivalent to the derivative of the first function plus or minus the derivative of the second function, whether it's a sum or a difference. So again, the derivative of the sum or difference of the two functions is the sum or difference of their derivatives. So if you've got this expression here, you just take the derivative of each one separately. Obviously, this needs to be rewritten as x raised to the power of 1/2. We know that this is equal to 15x, which I did there. I rewrote that first. We know this is equal to 15x to the 4th power. And then you've got, again, 0.5 times x, and then subtract 1 from 0.5. So that leaves you with negative 0.5 as the exponent. So that's what we're left with there for that derivative. If you're rusty on this stuff, just practice it. Like, practice the problems that I've done here. Just do a search on Google for, like, practice on taking derivatives. Give me all sorts of math teachers will have, like, just sheets and sheets of, like, practice problems online. If you are rusty, just take about an hour to just do this a bunch just to get it down, so that you have it down. So this is not what you're thinking about. You're just doing this to be able to do the things that we're expected to do in this class. This is just a tool that we use in this course. F prime of x. So that's the derivative of this expression. I just rewrote this again. X raised to the power of negative 0.5 is equal to 1 over x, the square root of x. I thought I'd left this out. I'm not going to cover this. So partial derivatives. So if you have a function that's of more than one variable. So if you have a function that's so if you have some value like production that's a function of both capital and labor, and you want to take the derivative to get the marginal product of just one of them, you basically leave the other variable alone and assume it to be just a constant. So that's not what I want to do here. So, all right, so here, to take the derivative of this with respect to x, you basically just ignore y to the fourth, and just think of it as you would think of as 11. So treat it the exact same way. So you take the derivative of x to the fourth, multiply the whole thing by 4, subtract 1 from x's exponent there, and then 11 and y to the fourth are just treated as a constant. So that's the only difference when you have more than one variable to take the derivative. You leave the other variable alone, treat it as a constant. That's the only thing you do if you're expected to take a partial derivative, which you might be expected to do, but I don't think I do expect you to do it. But just to know, just know that that is what you do. This is something you learn in more multivariable calculus stuff, and the basis of it is the same as the basis for the standard derivative. But obviously, relationships become more complicated than a two variable relationship, and you need a method to take derivatives there, and that's what the partial derivative is. Yeah. It does, but it depends on what you need, right? Like, so if you need x, then you take it with x. If you need y, you take it with y. If it was capital and labor, and you wanted the derivative with respect to capital, you take it with k, and then if you wanted it with labor, you would take it with L. Just leave the other one alone. Only difference. All right. So let's now move forward. So the production function lies between the extremes of the linear production function that has perfectly substitutable inputs and the Leontief production function that doesn't have perfectly substitutable inputs. They have to be changed in fixed proportions, is what's called the Cobb-Douglas production function. The Cobb-Douglas production function is given by this relationship here, and it's specified as capital raised to some power times labor raised to some power. So that is what's called the Cobb-Douglas production function, and it will capture the characteristics that we assumed that general production relationships have, based on what I talked about in the beginning of the course, with the increasing returns and the decreasing returns and everything that we saw in the graph. This mathematical relationship will have those properties. So A and B are constants. Unlike linear production functions, the relationship between outputs and inputs is not linear. Unlike the Leontief production function, inputs need not be used in fixed proportions. The Cobb-Douglas production function assumes some degree of substitutability between the inputs, but not perfect substitutability. And we'll talk more about that when we get into the long run stuff. All right, now let's look at the algebraic measures of productivity. Suppose a consultant provides you with the following estimate of your firm's Cobb-Douglas production function. So they've estimated that your production function follows this Cobb-Douglas production function. Again, this is something that can be estimated using statistical methods like we used in Chapter 3 to estimate demand. So again, you look at just like patterns of output with the different inputs, place those into a statistical spreadsheet, do a regression, and then you'll get that relationship. It's a little bit more complicated because it's not linear, and so the explanation of how to do that is beyond the scope of this course. But it is something, if you're interested in doing, can be done, of course, learning econometrics, etc. Anyway, so your production function has been estimated to be that. The average product of labor, of course, is equal to quantity divided by labor, telling us at any given amount of labor how much on average is everybody producing. So with respect to this relationship, it's quantity divided by labor there. So you've got that L raised to the 0.5 power divided by L. So that is equivalent to L raised to what power? It's negative 1/2. Yeah. Remember, L raised to the 0.5 power divided by L raised to the first power is equal to L raised to the 0.5 power minus 1. The exponents are being, you're subtracting the top exponent from the bottom exponent. So you're left with L raised to the negative 1/2 there. So that's what we have here based on the properties of exponents, which gets us to K raised to the power of 0.5, L raised to the power of negative 0.5. So the average product of labor and varying amounts of labor can be estimated via this relationship here. And it's going to also depend on the amount of capital that's being used, but we'll assume that it's fixed in the short run, of course. So that's how we can rewrite that. Again, properties of exponents, important. That's why I had to cover it. All right, so that's the average product of labor from, and then also this is equivalent to this, right? K over L raised to the same exponent is equivalent to K divided by L raised to the exponent. All right, so what is the average product of labor when 4 units of labor and 9 units of capital are employed? Well, we plug those in to get our total product, right? You got to get that amount of Q that you're going to divide it, that you're dividing by the amount of labor. So in this case, we have 6. So remember here, properties, order of operations, make sure that you do exponents first, then multiply. So that's equal to 6 there. Average product of 4 units of labor is equal to, in this case, 6 divided by 4, which is equal to 1.5. So there's different ways of approaching calculating this stuff. You can either formulate the equation for the average product of labor as we did in the previous slide, or you can do it this way where you figure out how much output is being produced and then divide by the amount of labor. Either way works, whatever, as long as you can figure out what the average product of labor is and what it means. What this tells us is that when you're using 4 units of labor, on average, each one is producing 1.5 units of output. The second approach is to plug in L and 4, L equals 4 and K equals 9 into that expression we figured out there. So that will also get us 1.5. All right, so marginal product. So marginal product is going to be the derivative, right? So for a linear production function, if the production function is linear and given by this expression here, then again, if you're just taking, let's say you're taking the partial derivative of this with respect to capital, you're just interested in the derivative of this with respect to capital. That means this is a constant. That means, again, the derivative of a constant is equal to 0, right? So this just drops out. You take the derivative of this, you've got k raised to the first power, right? Multiply the whole thing by 1. K raised to the first power minus 1, k is raised to the 0 power, which equals 1. So the derivative of this with respect to capital is equal to, well, it's A, right? So A is the marginal product of capital, and B is the marginal product of labor. So the marginal product of capital is equal to A, the marginal product of labor is equal to B. They're constant. So we didn't derive equations, right? Like in the other derivatives we took, like you had a variable in there which implied that as we moved along the curve, that slope of that tangent line changed. This is a linear relationship, and so the slope doesn't change. And so the derivative is constant. And so it's really easy to figure out what the marginal products are for a linear production function. It's just the coefficients on our capital and labor inputs. Again, this implies that the marginal product of an input is independent of the quantity of the input used whenever the production function is linear. Again, that means that the marginal product of labor or capital, the extra amount of output produced by employing either of the two inputs, is constant. Linear production functions do not obey the law of diminishing marginal product. The marginal product of an input for Cobb-Douglas production function does depend on the amount of input used, as the following formula reveals. Marginal product for a Cobb-Douglas production function, if the production function is Cobb-Douglas and given by this expression here, then the marginal product of capital is, well, all right, so we have to take the derivative of this with respect to capital. To get this, we must take the partial derivative with respect to capital. So using the notation, so this is a way to notate the fact that I've taken a partial derivative with respect to capital. You just kind of put that subscript for k there. Or if you take the partial derivative with respect to labor, you put the subscript L there to denote the partial derivatives. So the partial derivative with respect to capital, multiply the whole thing by A, subtract 1 from A, and then again, L raised to the B power, you just consider it a constant, so you leave that alone. So it's A times K raised to the power of A minus 1 times L raised to the power of B. Just leave that alone. And the marginal product of labor is you multiply the whole thing by B and subtract 1 from B and leave K to the A alone, which is what I did here. So recall the profit maximizing use of an input occurs at the point where the value of the marginal product of an input equals the price of the input. So we can use these relationships to figure out what that optimal amount of an input is. So demonstration problem. A firm produces output that can be sold at a price of $10. The production function is given by this Cobb-Douglas production function. Capital is fixed in the short run, though, at 1 unit. So if we plug in the 1 unit, then it simplifies the equation to just output as a function of one variable labor, which means you don't have to take a partial derivative. You just take normal derivative. So again, capital is fixed at 1 unit in the short run. How much labor should the firm employ to maximize profits if the wage rate is $2? So what is that relationship we're looking for again to figure out the optimal amount of labor? We're setting what equal to what? What was that thing called? The value? Value marginal product of labor, right? Equal to what? The wage, exactly. That's the relationship we need in order to figure out the optimal amount of labor. So again, first we plug in 1 because we're in the short run. We got to get our production function into the short run. 1 raised to the power of 1/2 is equal to 1. So we're left with this production function here. We need the marginal product of labor, right? So we take the derivative. So multiply the whole thing by 1/2, subtract 1 from the exponent. So the derivative is equal to 1/2 L raised to the power of negative 1/2. We need the value of the marginal product of labor. So what do we need to do to this to get it to the value of the marginal product of labor? Remember, it's the value of the output that can be produced by employing an extra person. How do we get the value of what can be produced? You know how much is being produced. You need to multiply it by what? The price it can be sold at, right? Which is what? That's the wage rate. $10. It's $10 there. We were given the information. So that's our marginal product of labor. Now that we have the marginal product of labor, we need to plug it into the expression that we need to get us a profit maximizing level of labor. So value of the marginal product of labor equals the wage. Multiply the price times the marginal product of labor. And that's going to get us to $10 times our marginal product of labor. Set that equal to the wage, which is equal to $2. And now you just need to solve for labor. So we divide both sides here by 5. All right. You have this variable you're solving for. In order to solve for a variable that's being raised to some power, you want to get rid of the power, right? In order to get rid of the power, you want to multiply the whole expression by something that's going to make the power equal to 1, right? So what's going to make this, what do you need to multiply this to equal to 1? Not just 2. Negative 2, right? So we need to therefore raise both sides to -2 to isolate your L, right? So again, you're multiplying -2 times -1/2, that equals 1, and then whatever that is going to equal, in this case, 6.25 units. So that means that you need 6 1/4 people in order to maximize your profits. Like if you hire 6.3 people, then you'll get into that area where the value of the marginal product of labor is less than the wage. So essentially, obviously, you hire 6 people because you can't hire 6 1/4 people because that would be inhumane. All right. So anyway, does everybody understand this method? What I did, how I got this? That's why I did all the properties of exponents and derivative stuff. A class like this normally will just expect you to just jump in. But I don't like to do that because I know that some people, maybe it's been a while since you've taken the class, the 103 class or whatever, so I like to do that. But now that I've done it, I've done it. And I'm not going to do it again. You're expected to know it. So make sure you do. If you're not good at it, get good at it. Now, not later. Now. All right, let's start talking about the long run, and then we'll call it a day. I have about 5 minutes. All right, so again, in the long run, all inputs are variable. So we have a way of sort of figuring out, like, how do we pick our input mix, amount of capital and labor, to minimize the cost of producing a certain amount. So our next task is to examine the optimal choice of capital and labor in the long run when both inputs are free to vary. In the presence of multiple variables of production, various combinations of input enable the manager to produce the same level of output. You can have a lot of capital and a little bit of labor, or a little bit of labor and a lot of capital, and that will get you the same amount of output. An automobile assembly line can produce 1,000 cars per hour by using 10 workers and 1 robot. It can also produce 1,000 cars by using only 2 workers and 3 robots. To minimize the cost of producing 1,000 cars, the manager has to determine the efficient combination of inputs to use to produce them. The basic tool for understanding how alternative inputs can be used to produce output is what's called an iso-quant. Iso meaning same, quant quantity, same quantity. An iso-quant defines a combination of inputs, capital and labor, that yield the producer the same level of output. So they look like this. They look like an indifference curve, right? An indifference curve represented various amounts of the 2 goods that the consumer could produce that yielded the same amount of utility. Here, the level of output is represented by all the combinations of our inputs that can be produced along this curve. And again, this means that 100 units can be produced with a lot of labor and a little bit of capital, or a lot of capital and a little bit of labor, or some mix in between. Again, the combinations of the 2 inputs along the iso-quant will yield the same amount of output. Iso, same, quant, quantity, same output, same quantity. So the figure will depict an iso-quant map. As we're moving along an iso-quant, we're substituting labor for capital. As we move out on the iso-quant map, the iso-quants represent higher and higher amounts of output. Like as we moved out from an indifference map, the indifference curves represented varying combinations of the 2 goods, the consumption bundles that yielded this higher levels of utility than those on indifference curves closer to the origin. So again, as we get further and further out, we have increasing output that each of these iso-quants represent. This one represents 200 units of output with varying amounts of the 2 inputs. This one represents 300 units of output with varying amounts of the input. The iso-quants are convex, meaning they have this shape like the indifference curves did. Inputs such as capital and labor typically are not perfectly substitutable, and that's what this shape captures. It captures the fact that they're not perfectly substitutable, which means that at varying levels of labor and capital, the rate at which you could substitute them for each other to maintain the same level of output will change. And we'll talk a little more about that as we move forward. If we start at point A and begin substituting labor for capital, it takes increasing amounts of labor to replace each unit of capital that is taken away. The rate at which labor and capital can be substituted for each other is called the marginal rate of technical substitution. So remember, the marginal rate of substitution was the slope of the indifference curve, the rate at which a consumer can switch out the 2 goods that they were consuming to maintain the same level of satisfaction utility. In this case, the marginal rate of technical substitution is the rate at which you can, as a firm, substitute capital for labor and still maintain the same level of output. And it's going to be changing as we move from left to right. In fact, it is diminishing. The marginal rate of technical substitution of capital and labor is the absolute value of the slope of the iso-quant, and is simply the ratio of the marginal products. So like the slope of the indifference curves was the marginal rate of substitution, which was equal to the marginal utility of the good on the x-axis over the marginal utility of the good on the y-axis, the marginal rate of technical substitution is also equivalent to the ratio of the marginal products in this case. The marginal product of labor over the marginal product of capital. The marginal product of the good of the input on the x-axis to the marginal product of the input on the y-axis. And we always assume that capital is on the y-axis and labor is on the x-axis. So that's a convention in this approach. All right, let's just call it a day, and we'll continue on with this on Thursday. Have a good couple of days. I will open up that homework, but again, we're not going to we're nowhere near close to finishing this chapter yet. So, if you read forward, yeah, try the homework. But if you're not reading forward, I wouldn't suggest it. All right, I'll see you. Have a good one.